Comes out of section 9.1, antiderivatives. Before we get into, a table of antiderivatives or table of integrals or anything like that that you'll be given on a formula sheet, let's try a couple, again, relatively straightforward ones where we're just trying to think about something backwards. So let's continue with what we were doing in the last one. Find the most general antiderivative of some function. So let's try this one. F of x equals e to the negative 2x. If you're looking at doing the antiderivative of that, hopefully automatically you'd think, well, I need e to the negative 2x, because when you differentiate an exponential, you get it itself. But if I took the derivative of this, I'd also end up times negative 2. So I need to somehow get rid of that, and this is the way I do it. So the answer to this one is e to the negative 2x divided by negative 2. Again, if you're not quite sure, figure out what the derivative of this is, and you'll find out that you get back to where you started. So let's try this one. What if f of x equals 1 over x? Well, if they don't give us the interval or anything like that, we'll say, well, the antiderivative of that should be the natural log of the absolute value of x, and again, plus c for the most general. If we're given something like this, f of x equals sine of 5x. Hopefully, again, given that we finished trig a week or two ago, everybody would start off realizing that we need a cos of 5x in here. But if I took the derivative of that, I'd end up, first of all, with negative sine of 5x, so I gotta deal with that. But I'd also have times 5, so I need to divide by 5. And the antiderivative that you get is negative cos of 5x divided by 5. And try it, see if it works, and convince yourself that it does. Now, let's go through this table of antiderivatives and see how it'll help us. If you have 0, the antiderivative of that is a constant. Another way to say that is the derivative of a constant is 0. Now if I have 1, the antiderivative of 1 is x. If I have a power here, x to the n, and I guess I should qualify that n doesn't equal minus 1, because that'll be a specific case that we'll do next. We'll try that one next. But if I have x to the n, I know that I need x to the n plus 1, but I also need divide by n plus 1. And we'll do some concrete examples of that, but we even saw an example of that in the last one. Now the antiderivative of 1 over x is the natural log ln of x. If we have e to the some constant times x, and clearly that constant can't be 0, otherwise we're dealing with constants again, we need an e to the kx, but we need to divide out that k term again. The last ones are the trig ones. If I have cosine of kx, again where k doesn't equal 0, I'm going to need sine of kx. If I differentiate sine, I get cos, so I don't need to worry about negative, but I'll also have this k to deal with, so I have this. And finally, if I have the other one, sine of kx, where k doesn't equal 0, I'm going to need cos of kx, but differentiating that would end up with a negative, so I need to deal with that, and I also need to deal with the k. This little table, or something very similar to it, is something you'd be given on any given chapter 9 or test beyond that, but you need to obviously know what to do with it, and that'll be what we'll look at more specifically in our next examples.